Hello students, welcome to lecture 19 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on Localized Surface Plasmon Resonance, or in short LSPR. So here is the lecture outline. We will first see what is Localized Surface Plasmon, and then we will see how to do the derivations of Localized Surface Plasmon Resonance conditions, and we will treat using exact theory of LSPR, that is mean scattering theory or Me theory. We will also look into the quasi-static approximation of LSPR. We will find out how to calculate the scattering and absorption cross section. We will also see how to handle the cases beyond quasi-static approximation, and towards the end we will see the characteristics of void plasmon and metallic nanoshells. So let us begin with localized surface plasmon. So we have seen in the previous lecture that surface plasmon are basically the propagating waves, which we call them as SPPs, surface plasmon polaritons. These are propagating dispersive electromagnetic waves which are coupled to the electron plasma of a conductor, and they are propagated metal dielectric interface. Now localized surface plasmons on the other hand are basically non-propagating, that is why they are called localized, and they are non-propagating excitations of the conduction electrons on metallic nanostructures which are coupled to the electromagnetic radiation. Now you can look into this particular figure here. It shows the illustration of a localized surface plasmon resonance. So this is a tiny metallic nanoparticle, and with light falling on it, with the electric field oscillating up and down, the electron cloud is also getting. So when the electric field is in this direction, electron cloud is basically pushed downwards. So that creates a kind of negative charge. All the electron clouds are pushed downwards, so there is a kind of negative charge here, you can say, and there is lack of electrons on the top side, so you can think of some positive charge formation there, okay, or there are some holes, you can say. In that case you are able to see some charge separation, that is positive and negative. So this actually becomes like a dipole, and as the electric field changes, when the electric field is negative, okay, you will see the electron clouds are moved upwards in this case. So you have the negative charges here, and the absence of the electrons are felt here, which are the positive charges, and so the dipole also got reversed. So that is how with the electric field this metallic nanoparticle gets a induced dipole that also oscillates. Now with that, what happens, you might know this fact that oscillating dipole radiates. Now in this particular case, this metallic nanoparticles, they also behave like dipoles which are oscillating with incident electromagnetic field. Now you can analyze this problem using a scattering problem of a small sub-wavelength size nanoparticle in an oscillating electromagnetic field. Now in this particular case, it is important to remember that the curved surface of the nanoparticle exerts the restoring force on the driving or on the driven electrons, so that they are pulled back, and that is how this oscillation will start. They kind of oval like a piece of jelly. So if you put a bulk of jelly on the table and try to poke it with a finger or a spoon, you will see that the jelly is kind of wobbling. The similar kind of feature is also seen for surface electrons in this case. So this lead to a field amplification both inside and in the near field zone of this particular particle. So inside and near field of the particles will get some kind of amplification of the electromagnetic fields, and that is what will give rise to resonance. So when this natural frequency of oscillation of the electrons matches the frequency of the incident field, there is a resonance. That means those metallic nanoparticles are able to strongly absorb or scatter light much larger than their geometrical cross section, and that is the phenomena of resonance, and we call that resonance as localized surface plasmon resonance, or you can say plasmon resonance, right. So, here what is the good thing as compared to the case of SPPs, that here you do not need to worry about the phase matching condition. So, you can simply shine light and excite the plasmons. So, localized surface plasmons can be excited by direct illumination. Okay. So, the physics of localized surface plasmon will be explored in this particular lecture by considering the interaction of the metallic nanoparticles with electromagnetic waves, and we will see how do we get to the resonance condition. Okay. We will also see the damping process, because whenever there is a resonator, there are some damping associated, okay, that decides basically the Q factor of the resonator. So, we will see how this damping process depends on the nanoparticle, different sizes and shapes, and how the interaction between the particles in an ensemble or in large assembly, they actually affect this resonance. So, along with that, we will also see what are the other structures other than say solid nanoparticles that support this kind of resonance. So, we will see that the dielectric inclusion in metallic bodies, or you can say that a void in a metallic surface, that can also support this kind of localized surface plasmon resonance, and also nano shells, they can also support. So, we will also look into these particular cases. Now, when you look for surface plasmon resonance, the plasmonic materials which are considered are basically gold and silver nanoparticles, because they are also particularly interesting because their resonance falls in the visible range of the electromagnetic spectrum. So, that gives you direct, you can see directly that the particles are able to transmit and reflect bright colors, and they are basically coming from absorption and scattering, which are enhanced because of the resonance. And this effect has been found several years back, maybe hundreds of years back. You can see like the Gothic stained glass in Notre Dame de Paris. So, there all these beautiful and bright colors are basically coming from gold or silver nanoparticles embedded into the glass. So, while making, they used to mix this metal to get these bright colors. These are basically the colors coming out from the resonance of the nanoparticles. Similarly, the Lycurgus cup, this cup looks different in color when it is illuminated from outside. It looks like a green cup, okay, but when the light source is inside, okay, that is the case when you actually see the light, that is what is not absorbed is basically coming towards you. So, in that case, from the white light source that is kept at the back of the cup, if you remove the plasmonic resonance that is at blue green, you will see that the only red light is coming out towards you. So, you will be seeing the cup as a red cup when the light source is behind, but when the light source is in the front, you just see the scattering, and the scattering resonance is at the blue green or simply green. So, the cup appears green in color. So, it is the same cup, but it looks different because of this plasmonic properties. Now, when we think of calculating LSPR, we need to first see is there any exact method of calculating the scattering and absorption from this particles, nanoparticles. So, the solution comes from the Mee theory. So, in 1908, scientist Gustav Mee, he was able to find an exact theory that can give explanation to the colors of different colloidal solutions of nanoparticles of different sizes. So, there was an experiment where people made colloids of different size of gold and silver nanoparticles, and all of them look different in color. So, there has to be some relationship between the size of the particles with the wavelength and the color they strongly scatter or reflect. So, that theory was known as Mee theory, And how it works? This works from the concept that Maxwell's equations are linear. So, you can think of a total field that is a kind of summation of the plane wave excitation plus the outgoing wave, that is the scattered wave, plus the standing wave, that is the wave inside that particular particle or void. So, Ghost of Me actually did the solution for spherical particles. So, on spherical coordinate systems, he was able to solve the coefficients for each of the wave by matching the boundary conditions, and he was able to find out the exact calculation of the scattering and absorption cross section by these particles. Now, how it works, I will not go into the complete mathematical description of Me theory. This can be found in this particular reference, the second reference as you see here, Bohren-Hoffman book. Okay. So, in this particular book, scattering, absorption and scattering of light by small particles, you can actually see the complete derivation of Me theory. So, I am just showing the important formula here that will help you understand how this particular theory is derived and it is working. So, time harmonic scalar wave equation, we can write it. So, what is psi? Psi is basically the electric potential, it is function of r here. So, this is the wave equation, del square plus k square, okay, times psi r equals 0. Now, electric and magnetic field, if you express them as linear combinations of the vector harmonics m and n, you can write m equals grad cross r psi and n equals 1 over k curl of m. Okay. So, these are kind of some relations with electric and magnetic field, but then if you try to use this particular equation for a spherical coordinates or a particle with spherical symmetry like a sphere or nanosphere, okay, you can actually write down this in terms of spherical coordinates. So, you have r, theta and phi coordinates, right. So, now you are also able to write down your psi, that is the electric potential, in terms of r, theta, phi as 3 different variables. So, you can separate these variables and say that this is basically r of r, theta of theta and phi of phi. Okay. So, these are the 3 variables and you can actually write down the equation now in this particular form. So, from here to here, by assuming that psi r theta phi is basically this function. Now, if you solve it only for the phi equation, you get phi equals e to the power plus minus I m small phi. Okay. You can solve it for the theta equation, you will come up the theta is basically associated Legendre polynomial. And when you solve it for the r function, that is the radius function, this is how it looks like, and r turns out to be square root of 2 by pi ZL kr, where ZL represents spherical Bessel function. And in this particular equation, you will see that you will require JL, that is basically spherical Bessel function of the first kind, which is finite at r equals 0, and for rectangular waves you can use it for incident and internal cases. Also, for the scattered waves you can think of spherical Hankel function, which is given as small hl. So, what is the speciality of this function? It can be written in the form of e to the power I kr over r, where r tends to, as r tends to infinity. Okay. So, you can understand that this scattered wave at infinity will die down, it will go to 0. So, with that you are able to express E and H of the incident field using the 2 vector harmonics m and n that you have seen here. Okay. So, you are writing them as a linear combination of these 2 vector harmonics. So, H incident and E incident are the incident electric and magnetic fields. Now, then you apply the conditions, like for a plane wave with incident angle theta equals 0, all the terms will vanish except for m equals 1. So, that gives you a simplified version. You can find out what is AL1 that term comes out to be like this, and BL1 is basically IAL1. How does it help you? You can actually use this similar kind of expression for scattered and the internal field. So, scattered field is also represented as combination of the vector harmonics. Okay. Similarly, internal fields are also written like this. I am not going into the description, but what happens after you find out the incident field, the internal field and the scattered field, you can apply the boundary conditions now. So, the boundary conditions say that the tangential component of the electric field and the magnetic field are continuous across the sphere boundary. So, if you consider the radius to be a, you can write that E incident plus E scattered minus E internal cross r cap equals 0. Similarly, H incident plus H scattered minus H internal cross product with r cap. So, there is the curl is also 0. So, this is how you can actually, this curl is actually giving you what? It is giving you the tangential components. Okay. So, they become 0. Now, you can write down μ coefficients as a size independent. So, x equals k naught a. Okay. So, a is the radius. So, x is actually containing the information of the radius as well as the wavelength of the incident light, and you can find out all this coefficient AL, BL, CL, DL, and that helps you to actually compute all these particular fields. So, what are the fields? Internal field and external field or scattered field you can find out from this calculations. So, from this you are also able to find out the amount of scattered light, amount of what is not scattered is basically absorbed. So, those kind of things you can find out exactly for a spherical symmetry. Okay. So, for spherical particles Mie theory provides exact solution. Now, this is what we have been looking so far. So, if you think of plasmon as an overall picture, we have seen bulk plasmon, surface plasmon and then particle plasmon. We have seen that for the bulk plasmon, the condition was that epsilon m omega should be equal to 0. So, that is where the permittivity of that metal becomes 0. So, this is the boundary and that happens at plasma frequency omega p. Okay, and the value is square root of n e square over m epsilon naught. So, here you can see all this, n is the electron concentration, e is the electronic charge, m is the mass of electron and epsilon naught is the permittivity vacuum. Okay. So, all these parameters are basically fixed. So, plasma frequency, bulk plasma frequency is also not tunable. Whereas, you can go to surface plasmons and this is the condition. We have seen that epsilon omega m omega plus epsilon d equals 0. So, the condition is basically epsilon m omega equals minus epsilon d. So, where they are matching, you are able to excite surface plasmon resonance, and here the surface plasma frequency actually becomes omega sp over. So, that is omega sp is equal omega p over square root of 1 plus epsilon d. So, you can reduce the frequency when you go to surface plasmon. So, our aim would be here to find out what is the resonance condition for particle plasmon or localized surface plasmons, and then what will be the surface plasma frequency in this case. So, let us look into a much more simplified approximation to Mie theory, that is basically quasi-static approximation. Now, what is quasi-static approximation? The name itself suggests it is quasi-static. So, for very small particles, when I say very small, the radius of the particle is much smaller than the wavelength. Okay. We can say that the phase of the harmonically oscillating electromagnetic field is practically constant over the particle volume, because the particle is very small. Okay. So, in that case, instead of electrodynamics, you are able to use electrostatics. Okay. So, you can actually think of this particular situation, that you have a homogeneous isotropic sphere of radius a that is located at origin here. Okay. So, this is the permittivity of the metal, this is the permittivity of the surrounding dielectric, there is the incident electric field E naught, radius is a, p is the particular point and this is angle theta. Okay. So, in this case you can think of Laplace equation. So, del square phi equals 0 and E is nothing but minus grad phi. So, you can solve Laplace equation to find out the potential in and outside the particle. So, here also due to azimuthal symmetry you can ignore the phi dependency and you can simply take the dependency of r and theta. So, again the potential can be split into variables like r of r, theta of theta, and then you solve the theta equation, it gives you again the legendary polynomial. So, theta equals PL cos theta, and when you solve the r equation you get r equals small r to the power L or r to the power minus L plus 1. So, in that way you are also able to write down what is the potential inside, that is phi in, that is inside the sphere, and also phi out, that is outside the sphere. So, these are the two expressions from these equations that tells you what is the potential inside and outside the sphere. So, these are the new coefficients that you have introduced. Now, there are certain things like phi in should be finite at the origin. Also, when you look at phi out, so phi out when it is too far, okay, it should be same as the incident electric field's potential, okay, assuming that the particle's effect is no longer present at a far distance. So, phi out is E naught z, which is nothing but minus E naught z. You can write it as minus E naught r cos theta, okay, as r tends to infinity. So, if you apply these two conditions, you will be able to find out the coefficients. So, you will be able to find out what is B1, okay. So, B1 equals minus E naught and BL equals 0 for all other cases when L is not equal to 1, okay. So, in that case you are able to find out one coefficient, that is B1. How about A1 and C1, okay. So, here also you can say that the tangential components of the electric fields are continuous. That means CL equals AL equals 0 for all the cases L is not equals 1. So, let us take the tangential components. So, minus 1 over A dou phi n over dou theta at r equals A, that is at this point for inside potential and outside potential they should be same. So, that gives you this kind of a equation. What is the other case? That the normal component of the electric field is also continuous. Here in quasi-static approximation the electric field, magnetic field does not come into the picture. So, we will be considering about the flux. So, the normal component of the flux will also be continuous. So, you can find out what is the flux here, minus epsilon naught epsilon m, and then you have this one which is E, basically dou phi in over dou r, and you are calculating at this boundary. So, that is r equals A. Similarly, you can put it for this one outside region, this one. So, this gives you this particular expression. So, you have two variables A1 and C1 and you have got two equations now. You solve for it and you can get what are the coefficients A1 and C1. The mathematics is looking bit messy, but it is not that complicated. If you are interested, you can always try this on your own. Else, you can simply take these coefficients from this slide, that B1 is minus E naught, A1 is minus 3 epsilon d over epsilon m plus 2 epsilon d times E naught, and C1 is basically epsilon m minus epsilon d over epsilon m plus 2 epsilon d times E naught. So, you have got all three coefficients A1, B1 and C1. So, now you are in a position to write down what is the electric potential inside and outside the particle. So, phi in is having A1 coefficient, phi out has got B1 and C1 coefficient. So, you can put those here and this is how it looks like. So, this is the potential inside the particle and this is the potential that is outside the particle. Now, there is something interesting in this particular expression of potential outside the particle. So, if you see, there is a distinct contribution coming from the electric field, which is the incident electric field, that is fine. And then there is an extra component that is coming into the picture from the particles point of view. So, if you look here, so this looks like there is a dipole and there is a potential because of this dipole. So, you can actually think of a dipole with a polarizability P, which is given by this expression. So, this term you can take as P dot R over 4 pi epsilon naught epsilon d r cube. So, when you equate these two, you will get that P equals this is the expression, and this can be written as, and this polarization is proportional to the electric field. So, that constant, okay, you can take as polarizability alpha. So, alpha is the term 4 pi a cube, then this one epsilon m minus epsilon d over epsilon m plus 2 epsilon d. So, if you, this can be written as 3 v, that is the volume of the particle. So, what is the volume v of this particle? 4 pi by 3 a cube. So, 4 pi a cube can be written as 3 v. So, this is basically the polarizability alpha of the particle. Now, with this particular expression, you can find out what is the resonance condition. So, you can see that the polarizability will experience a resonant enhancement when the condition that the denominator of this is very small. That means, when modulus of epsilon m plus 2 epsilon d is very small. So, you can now epsilon m is basically a complex, right, because it is a metal. So, metal in visible wavelength typically they have complex permittivity. So, in this condition, and what is epsilon d? That is basically the dielectric one, which is a real number. So, you can think of this as real of epsilon m omega plus 2 epsilon d will be equal to 0. So, this is a condition for the resonance, and it is also known as Froelich condition or Froelich condition. Okay. So, you can understand that this is the resonance condition. Now, if you consider the metal to be a Drude kind of metal, so epsilon m equals 1 minus omega p square over omega square plus I gamma omega, where gamma is the damping constant, and if you try to plot the modulus of this polarizability over a normalized frequency, the frequency is omega over omega p here. Okay. In that case, if you take gamma equals 0, okay, that you will give you a infinite, because then this term becomes 0 completely. So, you will get a asymptote, it is going up infinitely. But if you consider some finite value of gamma, then you will get this 0 for gamma equals 0.07 omega p, you will get this blue curve, 0.1 omega p you will get this curve, and 0.2 omega p you will get this curve. So, what you can see is that as gamma, that is the damping getting increased, the Q factor of the resonance decreases, the resonance position more or less remains same, but the width of the peaks are getting broader. So, that is what is more damped. Okay. So, now coming back to this slide to fill this vacant spot. So, the condition now we have derived that epsilon m omega should be equal to minus 2 epsilon d for resonance, or you can say epsilon m omega plus 2 epsilon d equals 0, and LSPR frequency is nothing but omega p over square root of 1 plus 2 epsilon d. Okay. So, this is how the resonance frequencies have shifted from bulk to surface to particle plasmons. Now, coming back to the point that oscillating dipoles radiate. So, you can actually find out the electromagnetic field which is associated with an oscillating electric dipole. Okay. So, this is the exact calculation, this is not within quasi-static approximation, this is a exact theory. So, you can see that H is nothing but this is the expression for H. What is N? N is the unit vector in the direction of the point of interest, and P is the dipole moment of that particular dipole. So, these two gives you the expression for E and H. Okay. So, from this you can see that in the near field the fields are you can say predominantly electric, because in the near field regime you will get mainly electric fields, and in the radiation zone, that is when Kr is much greater than 1, okay, the fields are of the spherical waveform. So, this from this particular ones, if you put these two conditions, so in the near zone Kr is much lesser than 1, in radiation zone Kr is much greater than 1, you can find out that the field in near field is mainly electric, whereas in the radiation zone or the far field zone they are of the spherical waveform. Okay. Now, coming back to the quasi-static, we have seen that we are able to obtain alpha, that is the polarizability of a particle. Now, what do we do with that? We are able to find out the scattering and absorption cross section using these two simple formulas. So, scattering cross section will be k to the power 4 over 6 pi modulus of alpha square, and CABS, that is the cross section of absorption, will be k imaginary of alpha. Now, if you see the values here, scattering is proportional to a to the power 6 and absorption is proportional to a cube. So, you can understand that for small particles absorption dominate over scattering, but as the particle size increases, scattering quickly gains and then it becomes the major contributing factor. Okay? And extinction cross section is nothing but the summation of the scattering and absorption. So, extinction means whatever is the amount of light getting lost or extinct. So, these are the two observations from this particular formula. Fine. So, you can also write down like this, like if you take a sphere of volume V which has got a metal permittivity epsilon given as epsilon 1 plus I epsilon 2, within the quasi-static limit you can write a simplified formula for scattering cross section as 9 omega over c epsilon m to the power 3 by 2 times V and then this particular ratio. So, epsilon 2 is basically the imaginary part of the metal permittivity and epsilon 1 is the real part of the metal permittivity. So, you can also find out what is the resonance here. So, again if you look into the plot, so this is basically extinction spectra of a 50 nanometer gold nanosphere. So, what is the difference here? So, the black curve is when the surrounding media is air. Okay. In this case epsilon m is the surrounding media. Okay. So, it is not metal, it is here it is surrounding media is epsilon m. So, if you put epsilon m equals 1, you will get this particular graph from this equation, and then red one is water, and n is the refractive index, that is 1.33. So, epsilon m will be square of 1.33, that is 1.69 I believe, and then the last one is for silica, that is n equals 1.5. So, epsilon m in this case will be 2.25. So, this is what we can see, that you are able to do the refractive index sensing using this kind of gold nanosphere, because the resonance peak position is getting changed. So, as the dielectric, okay, so there is a bit of this should be D, okay, or you can say this is medium. I will correct this later on. So, this is basically epsilon D. Okay. You can say it is a dielectric, or you can also say this is the medium. Okay. So, when epsilon D increases, the resonance frequency is also from here to here, the resonance frequency actually increased. Yeah, no, sorry, the wavelength actually increased, it means the resonance frequency actually decreased and your cross section of extinction actually increases. So, once again this is in terms of wavelength. So, wavelength is increasing means it is getting redshifted, that means the energy is getting reduced. You can also apply quasi-static approximation for non-spherical particles, something like nanorod or nano ellipsoid. So, in that case you can have 3 particular axes. So, you can consider this particular case is an ellipsoid. So, it will have 3 axes A1, A2 and A3. These are basically the semi axis. So, this is how the equations are correlated. So, you can find out polarizability in different directions, okay, for the 3 cases. So, if you consider the cross section to be same and only the length to be different, so there will be 2 different cases, so which are shown here. So, you can also have longitudinal excitation or transverse excitation of the electrons on the surface of such nanoparticles depending on their incident electric field polarization. So, the light is falling from the top, it has got a horizontal electric field, okay, like this. So, the electrons will also oscillate along the length of the nanorod, okay. So, this is a nanorod or nanoellipsoid, okay, and you will get one particular kind of polarizability. But when the electric field is coming from this direction, sorry, the light is coming from this direction with its electric field oscillating in this direction up and down like this, then the polarizability will be different. So, alpha I gives you the polarizability along the 3 direction, which has got a geometrical factor Li in this particular equation, and Li can be obtained from here. So, as you can see, this is a generic case for a sphere. L1, L2 and L3 are same 1/3, because summation of Li should be equal to 1. So, with this you are able to find out the polarizability of an ellipsoid, and if you plot the absorbance versus wavelength, you will see that for the 2 cases, okay. So, if you change the aspect ratio, that is the ratio of the height over the diameter of this, okay. So, as you change the aspect ratio, there is a large shift of the resonance. First observable thing is that in such a particle there are basically 2 resonance peak. So, one resonance, this particular resonance peak corresponds to the surface plasmon resonance along the length of the nanorod, whereas this one is along the transverse direction. So, this is called transverse dipolar resonance, this is called longitudinal dipolar resonance, and when you increase the aspect ratio of the particle, you see that the transverse peak does not shift that significantly, whereas the peak of the longitudinal plasmon undergoes much more redshift. Redshift means shift towards longer wavelength. What happens to the energy? Energy reduces, okay. Now, quasi-static approximation, is it good throughout? No. For very tiny particles or very large particles, it is a problem. So, let us look into the case of first very large particles where the particle size is more than 100 nanometer. So, in those cases you should go for Mie theory, because they provide you an exact solution in form of power series expansion, and quasi-static are basically the only the first order terms from that expression, okay. But however, for quasi-static to little larger particles, you can actually add some extra terms, like you can add some effects coming from redshift due to retardation, okay, then broadening due to radiative decay and some higher order resonance. You can add those terms to make your quasi-static approximation little bit more accurate. But always remember, for spherical particles, Mie theory provides you the exact solution. So, this is what we have seen, that if you start from 50 nanometer, where this is the size of the particle, your quasi-static approximation is pretty good, but slowly as you move towards larger particle up to here 100 nanometer, Okay, you will see that there is a red shift, there is a spectral broadening. So, these are the effects that comes into picture. So, there will be radiative decay that gives you spectral broadening. There is also red shift due to retardation, because when the particle becomes large, the initial approximation that the electric field over the particle volume does not change significantly, that does not hold good. So, there will be a phase lag between the electron movement from one end on the other end of the particle, because the particle size is large. So, all these effects will be considered, and they will try to make your quasi-static theory more inaccurate when you try to go to larger particles. Here is an figure that shows you that with the size of the particle and change in the permittivity, how the resonance wavelength is going to change. And here is the damping pathways for particle plasmon. Means there are two types of decay. One is by the radiative decay. The name itself tells you that there is a radiation through which the decay takes place. So, you will get a photon out of it. The other damping may be because of the non-radiative factors, that is, it is getting absorbed. Okay, and this can be of two types, like it can be interband from one band, from the D band to SP band if you go, and or it can be also intraband. So, within the same band you are moving from a lower to higher energy level. Okay. So, that kind of transition also can give you damping in this particular particles. So, overall you will be able to get broadening because of this. Now, if you come to the other end, like if you go to extremely small particles which are less than 10 nanometer in size, then also there is a problem. Like usually for particles which are smaller than the electron mean free path in a metal, say in gold the mean free path is 42 nanometer. So, it means an electron can travel up to 40 or 42 nanometer without colliding with another electron. Now, if the particle itself is smaller than 42 nanometer, what will happen? Before the electrons get collided with another electrons, they will actually hit the boundary of the particle, and that will actually give you additional damping. Okay. So, these are called additional damping coming from reduced mean free path, and that can be also empirically associated with some broadening and there is some simple formula that can correlate the damping constant gamma with the actual damping constant, plus A is a constant which is usually taken as 1 for isotropic cases, Vf is the Fermi velocity, and R is the radius or the reduced distance of the collision. If you are thinking of a thin film or a thin shell, you can take that shell dimension or thin film dimension as this R, and that will give you some additional damping, and that you can put it back into the Drude formula to get what will happen to this particular resonance. So, here is an calculation of such line width and dephasing time versus resonance energy, and this has been done for gold as well as silver, and as you can see that this line is basically me theory, and for the particles which are smaller like 40 nanometer, 60 nanometer, they are very much lying on the me theory. Similarly, you can also see from here. Okay. For extremely small particles, that is where the radius becomes 1 nanometer or so, that is where you have to remember that the classic electromagnetic theory will no longer hold good. So, you have to go for quantum mechanics to solve it. So, there the energy gained by individual electrons per incident photon excitation can be written as delta E, which is h cross nu over n, and that should be greater than or equal to kBT, and n is what? N is the absolute number of electrons in that particular particle. Fine. So, with that we understood that there are particle plasmons which are tunable, and what are the different damping mechanisms for this. And there is another sort of plasmon that is also possible, which is called void plasmon. So, void means if you take a sheet of metal and make a hole out of it, there also you will see that when there is light incident on this, they will, if the hole is sub wavelength, you are able to excite electron clouds to move on one side, so you will get positive on the other side. So, this behaves like a source of plasmon. So, in this case you swap epsilon m and epsilon d. So, this is the metal, this is the dielectric permittivity. If you swap this in the metal sphere dipole moment, what you got in the previous one, you get this. So, in this case the Froelich condition of the resonance also will get changed. So, it becomes epsilon d plus 2 epsilon m equals 0, or you can write epsilon m omega equals minus epsilon d over 2. That means you can also find out what is the resonance frequency, that comes out to be square root of 2 by 3 omega p. That is the resonance frequency for void plasmons are also different. Also there are two cases, like this, the sphere plasmon that you have seen, where it is omega b, that is the bulk, or you can say omega p, that is the plasma frequency of the bulk metal, over square root of 3. Here it is different, okay. There is an additional factor of square root of 2 coming into the picture. Now there are two possible hybridized modes for these two things to come together and create a shell. So, this is called a nano shell. So, in nano shell there are possibilities that they are in the anti-bonding kind of orientation. So, where the outside dipole and the inner dipole are in the opposite direction, or you can also have this case where the outside dipole, so you can see the outside layer plus charges, then this side also there are negative charges, they create one dipole. Towards the inner side you will also have another dipole, plus and minus. So, here both the dipoles are in the same orientation, so the overall energy is lowered, okay, and this is called bonding type of interaction, and this is called anti-bonding type of interaction. So, in this case, in this particular two cases, you will have two hybridized modes. The resonance frequency of these modes are given as omega plus minus, okay. So, this is how it is obtained. So, you have 1 plus minus 1 over 2 L plus 1 square root of. So, you can take L equal to 1 and find out what is the first order, okay, anti-bonding mode and bonding mode for this particular cases. So, they are also tunable because you can change the metal, you can change the shell thickness, and you can also get a lot of tunability out of this void plasmons, okay, or you can say nano shells. Void plasmons are this one. You can nano shells, if you remember from the initial lectures, they were the ones having the largest tunability. So, depending on your application, you are able to design nano shells that can give you, that particular resonance at that particular operating wavelength, okay. So, with that we will stop here today, and in the next lecture we will go into little bit of more details of this resonance effects. And if you have got any queries regarding to this lecture, you can always drop me an email at this particular email address mentioning MOOC on the subject line. Thank you.